Hello, in this video I'm going to talk about Hubble's law, which is the observational foundation of modern cosmology. This was the first observational evidence for the expansion of the universe that then led into the development of the Big Bang theory and all the cosmological description and models that we've got nowadays. So this was truly revolutionary stuff. And this was only about 100 years ago in the 1920s that Edwin Hubble pulled this together. The historical background to it is actually useful for seeing how Hubble's law came about at the time that it did. Prior to the 1920s, people still weren't aware that there were multiple galaxies in a larger universe. People thought there was just one universe, what we now describe as the Milky Way. That's what they thought was the universe. And there were those objects that people had classified as nebulae in the night sky, these fuzzy, diffuse, cloudy objects that we now know to be things like galaxies and planetary nebulae and globular clusters. So in the 1920s, during the Great Debate, people then realized that there were these external galaxies. The universe was a lot bigger than people thought it was. And that gave fresh incentive to then study these galaxies as they'd now been classified in greater detail. This is what Hubble was doing. I mean, a lot of people had been taking spectra of objects in the night sky for ages. So this wasn't a new thing. But Hubble was then particularly looking at galaxies and the Doppler shifts of the spectra of these galaxies. And he noticed a couple of things. I mean, the first thing that he noticed is that the vast majority of galaxies are redshifted. So that's telling us that they're moving away from the Earth. He also noticed that the further away the galaxy, the greater the redshift. Now, he wasn't looking at galaxies at massive distances here. This was the 1920s. They had less sophisticated equipment than we have nowadays. So he was looking at relatively local galaxies, but there was still this pattern, a clear pattern between distance and the recessional velocity. So this linear relationship between the two of them. And this is what then got put down as being Hubble's law, that the recessional velocity of a galaxy, so how quickly it is moving away from us on Earth, is proportional to its distance. So you can plot this out, in a graph. You can plot out your V against D. Obviously, this comes back to the age-old problem of how do you get the distance measurement to these galaxies. It's not an easy thing to do, but people were able, with better telescopes and the like, to observe Cepheid variables or supernovae or other such objects in these galaxies, get some kind of distance measure on them. So you observe these galaxies, you work out the Doppler shifts on their spectra. From the Doppler shift, you get the recessional velocity, as we discussed in a separate video on Doppler shifts. Then you plot them out and you get some kind of scatter like this. So there's a definite trend, but it's quite a wide spread. It's tricky to get a best fit on this. So the constant of proportionality that we're going to add into this is not that well defined just off of this method of measurement. But we've got some kind of relationship, linear relationship between these two parameters. We turn this into an equation and we add in Hubble's constant. Now, we need to make a distinction here between the Hubble constant and the Hubble parameter. So we've got two things kicking around here. So let's turn this into an equation first of all. Say V is equal to H subscript 0, so H0D. Now, the reason we got this H0 is you've got the Hubble parameter, which is called H, and the Hubble constant. Now, the reason we got two is the Hubble parameter is changing with time. So this is a function of time. The Hubble constant is then a snapshot. It is the value of the Hubble parameter at the current time. So this applies to all space, but not to all times. So it's just the current time. Applies to all space at the current time. Now, it's not changing very quickly. So in astronomy and cosmology, when we're talking about the current time, You know, if you're a few thousand years out, it doesn't really make any difference. You know, we're not going to be waking up tomorrow or next week and we got a completely different value for H0. You know, it is changing. H is changing with time, but it's all right to say, okay, let's try and work out what H0 is, and this is going to apply for the era that we're in, which is going to be spanning thousands, hundreds of thousands of millions of years. You know, it's not changing rapidly. But there we go. We've got these two different, this constant and this parameter, which you want to not get mixed up. And you quite often see people using these interchangeably when they shouldn't really. Right, the SI units then of H0, and we can see we've got meters per second for our velocity. Divide that by meters. If we divide by the distance, that means our H0 has got units of seconds to the -1. Now, on astronomical scales, this is not the most convenient unit to use for the Hubble constant. So we tend to use kilometers per second per megaparsec. And I'm going to come back to this in a moment. But it's turning a tiny number, so something in the order of 10 to the -18 or thereabouts, into something like 68 or thereabouts. So 68 is a reasonable approximation. 68 kilometers per second per megaparsec. That's a reasonable estimate for what the Hubble constant currently is. So that's a lot more manageable on the cosmological scale than saying, oh, it's like 2 times 10 to the -18 seconds to the -1. So that's why we use these different units. We're quite often talking about distances to galaxies in megaparsecs, so why not build that into the units? The range, though, for H0, I mean, you get people anything from sort of 50 to 80, really. I mean, it's a massive range. I think now it's sort of narrowed a bit, maybe 64 to 77, something like that. But it's still quite a big range that people come up with when they're trying to determine the Hubble constant. But this can give us our first best guess at the age of the universe. As I say, this is evidence for the Big Bang theory. This is evidence for the expansion of the universe, that you've got all of these objects moving away from us. So everything's moving away. We've got this outward expansion, which suggests that, well, if everything is expanding outwards as you go forwards in time, if we go backwards in time, we're going to have everything's going to be collapsing in. Everything's going to be moving towards each other in the past. So how long since everything was in the same place? That's kind of an obvious question. If we go back in time and everything's getting closer together, then when was everything in the same spot? That would be the Big Bang. This allows us to have a guess at it. So the time that it would take to get everything back into the same place, the age of the universe, will be the distance divided by the velocity. This is just a, finger in the air, stab in the dark, classical mechanics sort of approach on this. So, and if we do distance divided by velocity, looking at the Hubble equation here, that gives us 1 over the Hubble constant. So we can now do a calculation of the age of the universe. Now, it's a little difficult to get the age from using this 68. This is one advantage of having our 2 times 10 to the -18 seconds to the -1. You just flip that and you've got the age of the universe in seconds. But if we're dealing in this 68, how do we get from the 68 to the 2 times 10 to the -18? Well, if we've got 68 kilometers per second, let's just deal with that bit first. 68 kilometers per second is 68,000 meters per second. So that's taken us to meters per second per megaparsec. Now, how many meters are in a megaparsec? 1 megaparsec is equal to 3.09 times 10 to the 22 meters. So if we're going to do 1 over a megaparsec, so a megaparsec to the -1, then we have to do 1 over 3.09 times 10 to the 22, and that'll be meters to the -1. So we can replace our megaparsec with to the -1 with a divide by 3.09 times 10 to the 22, and then that turns it into, gets rid of that and puts some meters to the -1, which will then cancel with that meters. So this is how we end up getting that value there of 2 times 10 to the -18. So it comes out at, well, if I put those numbers in, 2.2 times 10 to the -18 seconds to the -1. So take the reciprocal of that, divide by seconds in a year, and we end up getting 1.4 times 10 to the 10 years, or 14 billion years, which is, you know, a sort of age of the universe that gets bandied around quite a lot. I think nowadays people go a little bit lower, maybe a 13.7 billion years, but you can see how this is all hanging together. Now, the expansion that's being described here of these objects moving apart, this is not galaxies moving through space, although they can do that as well. This is the actual expansion of space. So the space is expanding and taking the galaxies with them. So the analogy that often gets used on this is, let's bring up a new sheet for this, I've run out of space there, is baking raisin bread. So you start with a small bit of dough. So they say that's a little bit of dough that you stick in the oven, and you think of a few raisins that we've got. Let's just take some of them near the middle in a little cross formation. So they're set up in the center of your raisin bread dough. You put it in the oven, and when you're cooking it, okay, it gets bigger. The dough expands. Think of the dough as being space. So the one in the middle stays where it is, and then the others are being carried by the dough. These raisins aren't moving through the dough. They're being pulled outwards by the expansion of the dough. And this is what we're talking about in the expansion of the universe. It is the expansion of the space that's making things move apart. And, well, just to finish off this analogy, two things you don't want to get confused with in this analogy, and I think I've mentioned this in at least one other video, is the limitations of this is the universe does not have a center and it does not have an edge, whereas raisin bread does have a center and it does have an edge. So don't push this analogy too far. But in terms of the expansion of space, it's fine to at least conceptually see what's going on there. Now, this is why it was so important to be looking at galaxies when Hubble's law was being pulled together. You can't look at objects inside our own galaxy, inside the Milky Way, because you're going to get proper motion of objects, stars and other such things inside the Milky Way. You're going to get actual motion through space, whether it's to do with the rotation of the galaxy, whether it's to do with other relative motions, actual motions through space that are occurring inside the Milky Way. For Hubble's law, we needed two things. We needed greater distances, so you could see this relationship between velocity and distance. So we needed to get to greater distances. So that meant getting outside of our own galaxy. But you also needed to be looking at expansion of space rather than proper motion inside a galaxy and objects that are gravitationally bound into a galactic structure. So we needed to get outside of our own galaxy in order to be able to see this relationship that is Hubble's law. And that's what Hubble managed to do in the 1920s. So you needed to have that jump forwards from the Great Debate in order to know that these galaxies actually exist. Now, since then, looking at the Doppler shifts of the spectra of galaxies, this is not the only method for determining the Hubble constant. Other methods have been developed. This could be observations of the cosmic microwave background radiation. It's quite a common one. People will look at that, and based on those observations and subsequent calculations, they will then come up with other values for the Hubble constant. The trouble is, with all of this, there are more methods to determine the Hubble constant, which are becoming more and more accurate, but we've been left with conflicting values. We're not converging on one value of the Hubble constant. We've got some values which are, 68 or whatever. We might have another one which is 57, you know, whatever it may be. I'm just picking numbers from the range that the Hubble constant might be in. But we're making these methods more and more accurate, and the numbers aren't getting closer and closer together. So what is happening? What's gone wrong? Why are we not getting a better, clearer single value for the Hubble constant? Well, this is an unknown. It's not been resolved, and is another area of active research in cosmology. You know, is there something wrong with our cosmological models? They're saying, you know, wrong in the Big Bang theory. Is there something wrong with the cosmological principle? Maybe there's something there where we've got an assumption too far. We've assumed a little bit too much. Maybe there's a problem in general relativity, and there's something happening on these galactic scales inside the universe that, you know, is uncovered and is causing a problem in one method of calculation, but not others. So, you know, maybe we've got some whole new area of physics that we're not even aware of. Yeah, there's a lot of things happening here, and it gets complicated. I mean, you see how much is continually coming up on the news about things like dark energy. You know, when we're looking at the expansion of the universe and the rate of that expansion and how that rate of expansion changes throughout the history of the universe, there's still a lot which isn't known about all of this. You know, people don't know much about dark matter, dark energy, what's powering this expansion, and any acceleration in the expansion that's occurring. So there's a lot of unknowns, and yeah, this is all very, very active research. But the foundation to it all, Hubble's law, around about 100 years old, you know, that's where it all began. That is the revolutionary moment that started us on this path to describing the evolution of the universe. So yeah, it's profound stuff.